Welcome back, students. In the previous lecture we saw how do we use the merge sort technique to sort a given set of elements. We will be learning a different technique today, what we normally call as quick sort technique. By the name of it, the quick sort does not necessarily mean that it's quicker than the merge sort. It's basically in case of where the volume, number of elements is lesser, it has a better performance over the merge sort. The quick sort algorithm also is based upon the technique of divide and conquer, essentially when we will be dividing the given set of elements into partitions. Now the basic difference, one of the basic difference between a merge sort and a quick sort algorithm over here is that merge sort basically makes the division, makes the partition in the middle, in the middle of it, basically creating two almost equal halves. But that's not the case in case that's not the case with this quick sort. As we learnt in merge sort, the merge function basically in the merge sort algorithm plays a very important prime role, is basically more or less heart of the algorithm. In this case we have a partition function. The partition function over here basically is responsible for making the partition, making the division in the given set of this set of elements. So that partition may or may not be equal to half, so that's one. And second, at the end of every this after we complete this one partition, one run of this partition algorithm, at least we'll be definitely having one element in its correct position. So if I try to explain it in terms of some large array, so if this is my array, in this case what we do is that we select an element, let's say the last element, but remember, not necessarily that you have to select the last element. This element is also called as a pivot element. So the idea over here is that we'll use two pointers basically, and we'll start comparing from the first element. This will be my first element. So from first element we'll start comparing this first element with the pivot element, with the element that we have selected, and wherever we actually find that we have some element which is lesser than the existing element, we'll swap that particular element. We'll have actually two different pointers. We'll have pointer of I and a pointer of j. So wherever we find any element, wherever we encounter any element that we find is smaller than this element, so we'll make a swap till the j basically reaches n minus 1 numbers. Once we are done with this, what we will be doing is that we'll be taking this element and swapping this element with the element that's being pointed by I plus 1. So because of that, let's assume this is the position. This one element at the end of one go will be actually in its correct position, and also it will be basically dividing the entire array into two parts. So once we have divided the array into two parts, we can essentially apply our quick sort algorithm on this half as well as quick sort algorithm on this half. So that is the divide and conquer strategy. So what we have done is that, one, we have actually sorted one element. Two, we are able to actually divide the original problem into sub problems. Once we divide, then we try to solve the first half as well as the second half. Similarly, we'll be taking one pivot element over here, and using that element we actually use this partition algorithm to sort that one element, and that is the second half that will be that basically the other partition that will be created in this half. Similarly, we will be selecting the element over here and use that to partition this half. Now we can use quick sort algorithm on this half, quick sort algorithm on this half, accordingly, till we basically are able to reduce the entire problem, reduce the full problem into very smaller size problems. Those smaller size problems we can sort. If this problem is of a single element, let's suppose it's a of 1, it's a one element, single element. Now remember, the single element, let's assume it carries a value of 5 in this case. Now single elements are always sorted. You cannot sort any further a single element. So if you can actually reduce this entire problem to a level of unit elements, and then basically we'll find out that if I have solved all those such sub problems, then we have actually solved the entire problem. If I take this example in this case, I suppose we have a given set of numbers which contains a 14, a 1, a 9, a 0, a 5, and then 11. So this is my given array. This is the array. Now I'm using basically two more indexes over here. P will be pointing to the first element and R will be actually pointing towards the last element. So essentially this is my P, the first, and this is my R here, the last element. If we have a look at the algorithm, we are first selecting our pivot element. Pivot element in this case, in this particular version of the algorithm, I'm taking as the last element, but I reiterate again that it's not necessary that every time you can always take the first element as a pivot element, or you can take some other middle element as a pivot element, or you may take the last element as the pivot element. So here my pivot element X, I'm storing A of R, which is actually pointing to the value 11. So this is my pivot element in this case. Next, I'm using two indices basically, where an index is an I. Basically, this is pointed, since P is pointing to the first element, this is position number 1, position number 2, position number 3, 4, 5, and a 6th position. So my P is basically pointing to the first element. My I, this index, actually it will be pointing to something called as P minus 1. It's actually here somewhere. And my J, I will start a loop. Now this loop, basically the job of this loop is to traverse every single element in this array up to R minus 1. So it will essentially start from 1 and go to the position 5. So my J is in the beginning starting to the pointing towards what P is pointing towards. What we need to do over here is that I need to compare this A of J, here, whatever the J is pointing towards at one point of time. I need to compare this A of J with my X. It's important to understand over here. I will basically I'll emphasize on this particular point. The job of this J pointer is basically to select or to point towards different elements, towards all the elements that are there in the given array or given set of elements, and each such element will be actually compared to the pivot element. Now if we find out that the element that the J is pointing to, it's lesser than X, so that element, any element, say 1 in this case, or a 0 or a 5, if we find out that it is lesser than this, then we will increment our I index. So I will be basically incremented by 1 actually to point out to the next location, to the next element, and then we will actually swap the two elements, A of I and A of J. Whatever I and J is pointing towards, we will make a swap between A of I and A of J. Let's see in this example how it will work. I make a comparison of if A of J here is basically pointing towards a 14, is less or equivalent to X. Now my X here, less or equivalent to X contains 11. The condition over here is basically false. Since the condition is false, we are not basically executing this particular condition, and we're actually going back to the loop for the next iteration. When I make the next iteration, the J gets incremented by 1. Once I increment the J by 1, now my J is pointing towards second element. No change in I, just the J is getting incremented by 1 because of the loop. I again make the comparison. If A of J now is pointing towards 1, A of J here is pointing towards 1, is that less or equal to 11? The pivot element, the comparison is between the A of J and the pivot element. The condition in this case happens to be true. Now if the condition is true, what we need to do is that we need to increment our I by 1. So I will increment my I by 1. So I will now be pointing towards the first element. Once I make the necessary increment, I'll be making an exchange, I'll be making a swap between A of I and A of J. So I will swap A of I with A of J. I here is basically pointing towards 14, and my A of J is pointing towards 1. So I'll make the next necessary exchange. What I'm going to do over here is that I'll change the position of these two elements, and we're done. We'll increment the loop. J now points to the next element. It's my J now. Again, once we are inside the loop, we'll make the necessary comparison between A of J and an X. A of J is now pointing towards 9. Now my A of J here points towards 9, and my X, the pivot element, is 11. So again, the condition is basically true. In this case, 9 is actually less or equivalent to 11. So I'll make an increment towards for I I will be now pointing towards my next element. We'll make the necessary exchange between a of I and a of j. Once I make the necessary swap or exchange, 9 will come over here and 14 will go to location 3. Again, we are still in the loop, so j will be incremented and j will start pointing towards the next element. This is my j in this case, and now the j is pointing towards a 0. We'll again make the necessary comparison between a of 4, which is 0, and a of 6 or which is an 11. Since the condition is true, because a of j is right now pointing towards a 0 element, so in this case again you can find out that 0 is less or equivalent to 11, which is true. So I will make the necessary swapping in this case. To make the swap, what I need to do is that I'll be first incrementing the I. I will now point to 14. After the increment, once we are done with the increment, we'll exchange the two. So 0 will be now shifted to this, and a of 4 will now point towards 14. We are not still done with the loop, because loop has still to go one element, so we'll make the next increment in the j. In this case, my j will start pointing towards my 5. Again, we'll make the necessary comparison between a of j and the x. Since a of j is at this point of time is now pointing towards a 5, so the condition happens to be true in this case, so we'll make the necessary swap. But before I make the swap, I need to increment my I. So I will now be pointing towards 14. Make the necessary swap between a of I and a of j. So my five will be here, and I'll have 14 over here. Once j reaches this point of r minus 1, which is 5 in this case, we exit this loop, because we are done with the loop. We have exhausted all possible elements. Once we come out of this loop, we have to exchange now a of I plus 1. Now in this case, a of I is pointing towards location 4, so a of I plus 1 will be pointing towards location 5. This is the location which basically contains the value of 14. We make necessary swap between a of I plus 1 and a of r. A of r actually is my 11, or the pivot element. So what I will do is that I will make a swap here. This is my pivot element, and this is my a of I plus 1. Once we make this particular swap, then we can return the index back to the calling function of quicksort. Now what we need to understand is that after the completion of one go of this particular element, this 11 stands sorted. This particular element now is in its correct position, and more importantly, it has divided into two parts, not necessarily two equal halves, but two parts. Two partitions have been created, and one of the very important point about these two partitions is that all the elements towards the left of this particular element, all the elements towards the left of this are either less or equivalent to this particular element. So you can find out that every single element that's present over here is either less than 11 or is equivalent to 11. So all these elements on the left hand side are less or equivalent to 11. That's very important in this case. And all the elements there on the right hand side are necessarily greater than the pivot element. This is how basically your partition function works. What we need to do is that we need to find out the quicksort algorithm for this, and how exactly does that quicksort algorithm make call to the partitions, and how exactly are these divisions created. Let's try to go into the quicksort algorithm and understand how it works. Okay, let's have a look now at the quicksort algorithm. Now remember, as I said earlier, that the partition function over here is the most important function in this case. What quicksort algorithm essentially does is that we try, given by the index that's returned by this partition function, I get to know that where do I basically divide this set of elements, or divide the problem in this case, and whatever the value is returned from there basically decides that the two halves, the size of the two halves in this case. So essentially, let me repeat again, this is a set of numbers that's basically given. The partition function basically returns some point when I can basically divide the problem into two different halves, may or may not be of equal size. The left half basically will be solved by one quicksort function, and another half, the right side, basically the right partition, will be solved by another quicksort function. And if necessary, we will be making multiple certain more divisions as and when necessary till we reach those unit elements. Unit elements in basically are actually sorted elements, and at the end of the day, if you are able to divide this problem or reduce this problem to a level of unit elements, then we will have the actual array sorted. Let's take an example in this case and try to find out how exactly does this quicksort algorithm work in this case. It will be easier to understand if we take support of an example in this case. So let's suppose I have an array. Given set of elements contains elements 11, 3, 9, 5, 7, and 6. So this is the given array over here. As I said earlier, P is pointing towards the first element, R is pointing towards the last element. So this is my pivot element. Let's represent it by an X, and this is the array A. Now in this case, I need to find out that whether I need to make those partitions or not. So I am testing for P and R. Is my P smaller than the R? So P is actually pointing towards the first element, this is my second element, third element, fourth, fifth, and R is pointing towards sixth element. So once I see basically this thing, so I make a call to the partition function, which will actually return me my Q. If I make the call to the partition function, again we have two pointers, we have an I and we have a J pointer. J pointer will be actually pointing towards the first element, which is pointed to by P, and I will be basically to P minus 1. What we need to do over here is that we will be traversing all the elements of the array pointed to by J. We will be making necessary comparisons between all the elements with the pivot element. If we find an element which is smaller than the pivot element, then in that case we will be making an exchange between the elements that are pointed to by I and J till we finish the complete all the elements. Once we are done by that, we will be returning an pointer or an index pointed to by I, which we will store in Q, and given this Q, we will make the necessary partitions. So let's make the first pass. In this case, the first pass is that I compare A of J with my X. Now I can find out there that A of J is not less than X. The condition is not true, so I will increment J by 1. The loop will go increment J by 1, and I will make the necessary comparison. Once I make the necessary comparison over here, 3 is now compared to 6. The condition basically happens to be true, so we will increment our I by 1, and we will make the swap between A of I and A of J. Now A of I in this case contains an 11, and A of J in this case contains a 3, so we will make the necessary swap between the two. Okay, so this is my A of I now, and this is the new A of J. And again we will make the increment in the loop. J will now point towards the next element, that's the position 3, which contains an element of 9. I make the comparison of A of J with my X. Now 9 is not less or equal to 6, so we'll make a pass and we'll not make any exchange or swaps. We'll just increment our J again. Once I increment my J again, what I see is that now A of J, that's A of 4, is now containing 5, and if I make a comparison of 5 and a 6, so 5 is actually less or equal to 6, the condition is true. I will increment my I. Once I increment my I, now I will make the necessary swap between I and J, A of I and A of J. So 5 will come here, and my 11 will go to this place. I will keep on incrementing my J, which will now point towards 7. Again I make the necessary comparison of A of J and X. Now a of j is pointing towards 7 and I make it comparison with 6. The condition is false. A of 5, that 7 is not less or equal to 6. So we come out of the loop. We just increment our I, and I will now point towards position 3, and we will now swap a of I plus 1, which is now 3 in this case, will be swapped with the x or the pivot element or a of r. So I made the necessary swap. 6 will come to this position and 9 will come to this position, and that's at the end of the first pass. And remember, this I is pointing towards location 3, index 3. So essentially after the completion of first pass, we'll get the value here of 3 in this case, right? We'll make the new quicksort function calls. So more or less, if I have to put it like this, I can say I made the first quicksort call an array I had with p and r. So first element was p, last pointer was 6. So this is the first call when we started it. We made a call to the partition function. So this was my partition function basically, which had a 1 and a 6. We waited for the partition function basically to return the index value in this case. So we can find out that there were 2 more calls. There was a quicksort call to this array, and there was 1 more quicksort call. Now remember, in this case, that I cannot set the pointers, I cannot set the indices, I cannot say where do I make the divisions unless I get that value from the p. So once the p returns that value, then only I can make the necessary index values. I can write them down. So after we check the first pass, we saw that p in this case basically returned us a 3. The I is now pointing basically to the value of 3. So what we do is that we find out where do I divide this set of elements. Now the first call, the first recursive call here is p, that's a 1, and q minus 1. Now what's very interesting over here compared to other algorithms that we have studied earlier, we used to find out their q minus 1 and we will start from the next very element. In this case, the element 6 is already sorted. This is in its correct position. It does not be moved or swapped anymore because it's already sorted. So we do not take into consideration over here the value of q. See, we finish the first part with q minus 1 and we start the next part with q plus 1. So that gives an indication that the q is already basically sorted in this case. So what I am doing over here is that it starts with a p, that's a 1, and q minus 1. Now 3 minus 1 is my 2, element number 2, and the other call to the quicksort function is q plus 1, that's 3 plus 1 is my 4, and my r is just 6. So division is basically, this is the point where we have divided. Now this is the left half and this is the right side. What we need to do is that we'll make now a quicksort call to this half and we'll make the quicksort call to this half. When I make the quicksort call to this half, so it will go to the partition basically with 1 and 2, then its own quicksort calls. Let's first complete the partition call, then we'll complete the quicksort call. Likewise we will do with the rest of the elements. Once I make the partition calls over in this case, so we have 1 and 2. What we do is that my I in this case, my 5 is my pivot element, this is my x, it's my new pivot element. My j is pointing towards the first element and this is my I. We make the necessary comparison of a of j with an x, is this smaller than the 5. Now what I can find out that is a of j. It's very interesting to see over here how it works, because since we have only a single element in this case, so let's see how it works. A of j is at this point of time pointing towards a 3, value of 3. I make a comparison of a of j with my pivot element, so I find that 3 is actually less than 5. The condition is true. When the condition is true, what I need to do is I need to make a swap. But between which 2 elements do I need to make the swap? Before I swap, I need to increment my I. So I increment my I and I find out what an interesting fact, that both I and j, they are actually pointing towards the same element. So it's a single element which is represented by a of I and a of j. Since both the pointers, both of these indices are pointing toward the same elements, gives us an indication that it's a single element, and single elements are always sorted. That's where we have learned. So this element is already sorted in this case. So once this element is sorted, what we need to find out over here is that I go the loop gets completed because j has traversed all possible elements. That's a single element in this case. J has traversed all the elements, and it basically will now return its next value. The next value it will return over here is that I plus 1. Now what's that? I plus 1 will be pointing towards 2. I can find out over here is that the partition element that it transfers over here, I'll put it here, is 2. This is the element that the partition has returned me back. So my essentially call will be here P, which is pointing towards my 1, and Q minus 1, which is also Q minus 1. Q minus 1 basically it has returned a value of 2, minus 1 basically is a one single element. So it's a one single element, quicksort of 1 and 1. It's a one element that's both the pointers are pointing towards, and likewise we have a quicksort call over here Q plus 1. Now what it has returned us is a 2, and that's 2 plus 1 is a 3, and our R, which is 2. Now what you need to understand over here is that this quicksort call is towards an element which has an which is beginning from 3 and ending at 2, which logically is not possible. You cannot have an array that starts with a 3, that starts from here but ends here, which tells you that the element at this place is actually already sorted, so you do not need to worry about these elements. If we look at the other half of this side, this is one side basically, this is already sorted. If I look at the other half of this here, so it will make the partition call first, and it makes the partition call. The partition call here is between over here my 4 and my 6. Now my element 4, index 4 is pointing towards this element and 6 is pointing towards this element. I will select my new pivot element. The new pivot element in this case, here is 9. That is the x. J will now be reset and will start pointing towards the first element, and I will be pointing towards P minus 1. That's here. But this is my new P in the half, and this is my new R. Let's start from this particular element. Now J, here we'll make comparison between A of J and X. What we find in that case is that A of J is actually greater than X. It's not less than X. So condition is false. What we do is simply that we make an increment of J, and we do not do anything with the I. Once I increment my J, what I see is that I make a comparison between A of J is less or equal to X. Condition is true because 7 is actually less or equal to 9, so condition is true, and I increment my I. Now my I is pointing towards 11, and I make the necessary exchange. So my 9 is here, and this is my 11. Oh, I'm sorry, almost made a mistake. This is my 11, this is my 9. I have to make an exchange between A of I and A of J. So this is my I, this is my A of J, so I'll make the swap. This is 7 and this is 9. Now that J is pointing towards an element which is R minus 1, that gives an indication that it has already exhausted all its options. It has traversed all the possible elements. What I do is that I take the next element, that's I return the pointer. The pointer in this case happens to be my I plus 1. I plus 1, I is currently pointing towards 4. It will now point towards my 5. That's I plus 1. So it should now return me a 5, which gives me a quicksort call of element over here P, which is a 4, and Q minus 1, which is a 5, but 5 minus 1 will be again a 4, which is a singleton element, in this case this 7, and there will be another quicksort call that will be between p1 and 1, that's 5 plus 1, that's a 6, and r, which again is a 6, which again points to a singleton element. But you can find out here in this case that by the time we reach these last elements, we have already a sorted array in the form of a 3, 5, 6, 7, 9 and 11, which is a sorted array. This is how exactly your quicksort algorithm works. About the complexity of this algorithm, we need to understand that every time the J has to traverse all the possible elements, that gives an average of an order of n comparison, order of n moves that it has to make, and we need to find out the divisions. Now the divisions can be tricky in this case. We can have divisions of like this, wherein it gets divided into two equal halves, and both the halves basically get so equal number of levels of divisions we get, or else we may have a division of something like this, something of this type. So we get a division over here, and then all this part gets divided. Next division we have one element here and all the rest of the array is here, and we get one more element and all the rest of the array is here. So it may work like that, whereas again we'll be having some order of n, which will give us a total of order of n square in worst case. And if we have an equal division just like this, then it will be in terms of an n log n. Hope you understood how exactly quicksort algorithm works. This was the last topic in divide and conquer strategy. In the next lecture we will take a different topic. Till then, take care.